might become relevant later on. Like, it's not just that, oh, like I can identify it, but more so what's the point of identifying, and what does that part actually add to the structure, like the function of a certain structure, I think.
Yeah. Yeah, it sounds about right. Oh, but even then, like now we don't actually do a whole ton of stuff either. I think it slowly becomes a bit easier though, like as you cover more histology, you get to recognize what's, you get to recognize where some tissues are. RJ is Kishi.
What?
All right, cool.
How many should we have? We should have 22 in the Kahoot. Yeah. When is your HKS assignment, you guys? Next week, 20th? Oh. Okay, next week. How's it working for you guys since you, like, are you still giving a presentation or what's happening? Okay, group essay.
Group essay, we love that.
Group essay for HKS. What was the HKS assignment about?
It was like you choose a topic on public health in Australia. Like you choose your one, remember?
Okay.
Is this everyone? 18?
We should have more, but I don't know. You can probably start.
Okay, I'll just start.
Health system impact due to COVID-19. Classic. Ah, so everyone's doing the same topic, but a different country. Okay.
Oh, that's pretty cool, actually. All right, come on, guys. Do me proud with these questions. Oh, okay. Let's go through this one. So the question says, select the true statement. And most of you guys said vasculature coordinates with the immune system, and that's exactly right. So vasculature, oh, did I write the question wrong? Surely not. No, this is right. Yeah, so essentially arteries don't have valves. Like obviously that's wrong, right? Like your veins have valves to prevent backflow. So arteries have valves. So the yellow one is capillaries, arteries, and veins all have 3 layers of protection. So this isn't exactly right either, as capillaries are only usually like a very thin layer of what we call endothelium. Arteries and veins actually do have your interna, your media, and your adventitia. So those are the 3 layers. Capillaries do not. Your green one, collagen fibers connect arterioles and venules. That's all right either, as capillaries can actually connect the arterial and venules on the venous system and the arterial system. So ultimately, this kind of leaves you with vasculature coordinates with the immune system. And an example of that includes
the adhesion, where your lymphocytes will run through the blood vessel, and then they'll adhere to the endothelial layers, and then kind of slip through the endothelial cells into the tissue. So the vasculature, where the lymphocytes are running through, is helping with the immune system because it allows the delivery of those lymphocytes to the damaged or infected tissue.
Awesome.
Right.
So where can oxygenated blood be found? There's two answers, by the way. Ah, very good. So most of you guys got it right. This is like actually got to do with a little bit of like embryology. I'm not sure if you guys have covered it. So it's a little bit of reverse logic in this case. So pulmonary artery carries, because it's an artery, it carries blood away from the heart. However, since it's carrying blood away from the heart through the right ventricle, then it is actually deoxygenated blood. Likewise for the umbilical artery, except that's with the maternal body. Aortic arch obviously is pumped up from the heart to oxygenate the body with oxygenated blood. Umbilical veins actually is referring to the mother's body, so carrying the oxygenated blood from her body to the child. So that's why it's also oxygenated blood. Good job. I hate his dog. What a mood. Very nice, everyone. Pretty straightforward, this question. It's kind of just remembering simple squamous epithelium, think to epithelium as being this like very thin layer, especially in these vessels. Easy. Nova's mom. Who's Nova's mom? We love Nova though. All right, slightly longer question. I put the timer longer too. Think back to your 3-4 chemistry knowledge. Okay, so a bit difficult this question, but let's go through it. So question 1, why is this actually correct and not false? So a drug will not work unless it is, a drug will not work unless it is bound to the site of action. So, wait.
It's the false statement, David.
Did I write this wrong? Sorry. That is actually true. No, yeah, that is my bad. A typo in the thing. There was too many false negatives like at 7 a.m. in the morning. I will change that and I will post something out in the Facebook chat. So let's just move on for discussion for now. Like I'll write an explanation for this in a sec, just after.
Okay.
Sorry guys, like got tricked myself. Awesome. So affinity, like I always think about affinity and like your relationship between people. Like if you're really close with someone, then your affinity is like really high. Likewise, this is with drugs and receptors. Nice. So agonists, we want like agonists, agony. So it's like causing something. So it will be needing to bind to the receptor and actually cause an effect. So cancer drugs, like think about cancer as being this kind of evil villain that does everything that it can to become, a better version of your cells, even to a certain degree, right? So no contact inhibition because it can just like grow everywhere. And this is like often where it breaks through the basement membrane and then changes the cytoskeleton. So there's a lot of changes there on a like biochemical level. Enlarged nucleus due to the expanding protein production and needing for new DNA synthesis and just really constantly grows. And it's actually, so increased growth factor requirements. It is not a feature because it actually has decreased growth factor requirements. So it can grow really fast. Nice. So it's a bit of a split between oncogenes and proto-oncogenes. So let me just search out what onco prefix actually means. So in English, like onco just means tumor or malignancy, right? So oncogenes is like the occurrence of that mutated gene. Whereas proto-oncogenes, proto meaning like before or like the original / early stages of. So that's actually not where the types of the mutation does not occur in these genes. So in oncogenes, that's where the actual mutations occur. Great. So this is just kind of a recall question and identify where like mismatch repair genes work and like where P53 works and all of these things. Just flashcard this, like I don't have too good of a way to memorize this. Great, awesome. Everyone got that. Mostly everyone got that right. So essentially, oncogenes only require one allele mutation. So think about what I said before about like cancer being like the evil villain, the boss, right? Like it's always trying to find the easiest way. So it doesn't need two; it only need one to stuff up, and it can just run rapid. Once again, another recall kind of question. Awesome, really good. This is just one of the things to know, and it might come up on the exam as well. Should be easy marks now for you guys. Also, I see that Mrs. C ethics assignment reference. So I acknowledge that reference. Okay, so what is the first stage of cancer metastasis? So let's break this down. So firstly, between yellow and green, what most of you guys said. So cancer develops in size until breaking out of neighboring tissues versus cancer cells excrete enzymes which break through capillaries. So I think like it actually needs to break through capillaries first before actually breaking out towards neighboring tissues. So tissue is kind of a larger structure than we think of capillaries, and capillaries are more ubiquitous or like more prevalent around different areas or locations in which cancers might grow. So capillaries would be first, and then we would get to this neighboring tissues. Coolio. Easy. So it's like VEGF. What does it stand for? Vascular endothelial growth factor, or something along those lines. So VEGF, right? Like you gotta eat your veggies to get stronger, and essentially that's like the same for cancers. Like they're like gotta get all of those blood to like grow big, you know. Yep. So eat your greens, guys. Yeah, I'm pretty sure you guys did this in your quiz or something, so it's good to see the fast responses and you remember. Nice. So it's not quite malignant yet, and you can just tell from the silhouette of the image. Yeah. Yep. So bilateral development of cancer, like usually if you think about cancer, like it's one side, right? Like a part of this organ, like the DNA replication or something goes wrong, and then that causes this cancer to grow. Whereas bilateral, like both sides happening at the same time, like this ain't a coincidence. It's because of a genetic predisposition. Easy, good stuff, guys. So essentially, just like 100% penetrance just means that have the disease gene expressed. So more clinically, what does 100% penetrance looks like? So for example, if a patient comes in and you do a per rectal exam, so that's just like sticking two or one fingers up the rectum to check for bumps, then and you feel it and you ask them in the family history, which I'm sure you guys all now, like did your father or father have any colon cancer history, and they say yes, then a lot of times it's 100% penetrance that the offspring will also have it, which like the diseased gene will be expressed, like they will also express these bumps on examination. Yep, awesome. Oh, okay. So a bit of a more trickier question. So what is leukopoiesis not stimulated by? Um, so this is kind of a trick question in the sense that the other three, so like red, blue, and green, all stimulate leukopoiesis. The yellow one I just made up, so it doesn't exist. This is kind of just understanding the actual terms, which will impact your reading of the questions on the exam. Smiley face on top. All right, so some bit more of HKS here. Really good, good guys. So think about Gobi FFF, like we'll talk, I think we talked about it last week. So it's about selective primary healthcare, right? Like we're focusing on one group. Food supplements, female education, and family planning, like often they're related more to a maternal side of things, whereas farming is also more of a male-dominated kind of task, especially in a lot of these developing countries that Gobi FFF is implemented with it. Okay, so 2 more questions. Great, good. Good to see most of you guys have been listening in Clean Skills. So the difference between the red one and the orange one, or the yellowish one, is like the BP when your heart is relaxed and filling up with blood, that is what we call diastolic filling. So that's like isovolumetric relaxation. And essentially all of these things you'll learn in second semester when you're doing cardio. But systolic, think about the higher one, and like when you're like pushing something out, you have more pressure in order to push it out. Whereas when you're feeling it, like you're super chillaxed, like, you know, the blood pressure will be lower. And that it's like sys on dia, so it's like systolic on diastolic. So diastolic is the lower one. Lucky last. All right, so a bit of a harder question. Like I actually had to find out the name of this guy again. I just think about it as the first click. I was so stressed before doing this CSSE. I was like, oh my God, what if I fail this? But I turned out all right. Very good. So the way that you think about doing clean skills, especially taking blood pressure, is like you do it. So you boom, 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 right? Like you push it up until, like you can push it up until, for example, almost to 200, and then you'll start coming down, and then you'll click. Like that first click, or what we call the Korotkov sound, is the systolic blood pressure. And then when it around the fourth click, like it's starting to diminish, that's the diastolic blood pressure. So when you're looking at it, just kind of listen to what the first click is, and that's your systolic.
I mean, like it'll be a bit difficult because you don't have the equipment at home, but
that's true.
When you get to second semester and you actually do your vital signs, then we'll probably go over it again.
Yeah. And like for this one, most of the times, like I don't even listen for sometimes I really listen for the clicks. I just look at the wavering of the sphygmomanometer. Yeah, the pressure meter.
Yeah, that one.
Sphygmomanometer. But yeah, we'll go through it again when you guys when we meet you guys in person. Awesome. So now we'll just head on to the slides. Oh, who won? Yes. Smiley face. Oh, mindfulness number 3.
Oh no,
very
that's
good.
Number 3.
I hate histolog. I respect that.
Whoa.
And the big man or girl themselves is smiley face.
Very nice.
Very good.
All
Good
right.
job.
I love Captain Kane doing the runner-up. Good.
Yep. All right. Okay, so we'll make a start on the week 8 content, but does anyone have any questions from the Kahoot? Any questions, or like how have your neurotransmission ones been so far? Pretty okay, I'm gonna guess, I hope. All right, let's make a start then. Okay, so we'll be starting off with neurotransmission, and we'll be talking about 2 different types of nerves essentially. So your cholinergic nerves and your adrenergic nerves. And we'll start off with like an overview of what these different types of nerves are like. So we can see here that we can group them into 3 different groups. So we have your parasympathetic nervous system and your sympathetic nervous system. And you can view these as kind of opposites to each other, or they kind of balance each other out like you're on a seesaw. So your parasympathetic nervous system is going to be your rest and digest system. So hopefully that would be you right now. Your heart rate is fairly steady. It's probably closer to its resting level. Your blood pressure is not too high. You're not sweating too much. Your pupils are constricted appropriately. You're salivating. You're probably digesting your dinner. Things like that. And then essentially, if you think about all the opposites, that'll be your sympathetic nervous system. So that'll be your heart's racing, your blood pressure is super high, your pupils are dilated, you're sweating like anything, you're not salivating, you're not going to be digesting. So it's everything you're going to be doing when you're super stressed out. And then outside of these sympathetic and outside of your sympathetic and your parasympathetic, you'll have your somatic nervous system, or your somatic motor nervous system. And this here will be, this somatic system will be your voluntary muscular control. So me bending my arm here is through the somatic nervous system. And I'll be looking at the different types of nerves and the different types of neurotransmitters that we use for each of these 3 systems. So I shortly mentioned we have cholinergic and adrenergic nerves. And what these 2 things mean is we'll be looking at this end. We'll be looking at the neurotransmitter that is released at the postsynaptic, at the postsynaptic neuron. So this first neuron at the top is what we call the presynaptic neuron, because it all comes before the synapse here, or where these triangle-y looking things in the circles are. So we look at what neurotransmitter is released from the postsynaptic neuron. And we can group these into largely 2 groups. We have acetylcholine found here. We have acetylcholine found here and here. And there's one for sweat glands, but that's a bit of an exception. So these 2 ones where we release acetylcholine are what we call cholinergic nerves. The adrenergic nerves are the ones that secrete norepinephrine, or noradrenaline. Noradrenaline and adrenaline kind of interchangeable in this context. So you can notice that adrenergic nerves generally control our sympathetic nervous system, whereas our cholinergic nerves generally control our parasympathetic nervous system, as well as our somatic motor nervous system. However, there are exceptions to that, namely with our sweat glands, which is one that is shown in this image here. With our sweat glands, acetylcholine will be triggering us to sweat. So this is an exception because sweating is part of our sympathetic nervous system, and yet acetylcholine is activating that response. So that's a bit of an exception to take in mind here. Another characteristic of the sympathetic and the parasympathetic nervous system is the length of each of these neurons. So in our sympathetic nervous system, our preganglionic neuron is going to be quite a lot shorter than the postsynaptic neuron. Compare this to the parasympathetic nervous system, where the presynaptic neuron is going to be a lot longer. So as you guys start to do more anatomy, probably more so next semester, and once you kind of get into the thorax and the abdomen, thorax at the very end of the year, and you look like right next to your spine. So if you were to cut down the middle, remove your lungs, remove your heart, remove all of the junk inside, you're likely going to see two kind of chains. And these are your sympathetic ganglionic chains. And these are the connections between these sympathetic nerves, essentially. So since the preganglionic neuron is really, really short, that's going to just come out of the spinal cord and then synapse. And then you're going to have a super long postsynaptic nerve going from next to your spine all the way through to the gut and innervating that, or innervating your heart, things like that. But if you compare that to the parasympathetic nervous system, one nerve is going to come out of the spine, it's going to travel a long distance, and then once it's just about at the organ, then it's going to synapse. And then the postsynaptic neuron will be super short, and that'll attach to your organ. So the main difference to take from that is your parasympathetic presynaptic neuron is super long, whereas your sympathetic presynaptic neuron is super short. And that's the main idea to take from here. Okay. So we'll be covering adrenergic nerves first, or your sympathetic nerves, kind of interchangeable in this context. So as you can see from this top image here, you'll probably get a lecture from Wayne Hodgson if you haven't already. Your presynaptic neuron will be releasing acetylcholine, and then your postsynaptic neuron is going to be releasing noradrenaline. And this noradrenaline is going to be acting on the target organ or the target tissue. So we'll talk about noradrenaline for a bit. So noradrenaline is the neurotransmitter released, and this will be synthesized. This will be synthesized through a kind of a biochemical pathway. Can someone check the chat, please? David or Ajay. So this will be made through a biochemical pathway from tyrosine all the way down to noradrenaline and adrenaline. You don't need to know all of these enzymes here. The main important one to know is that tyrosine hydroxylase is part of that process. So know that tyrosine is a precursor. Tyrosine is a type of amino acid, I believe. And it goes through this giant pathway and it ends up at adrenaline and noradrenaline. Something else that is important to take note of is that noradrenaline, one of our products, is going to be inhibiting our tyrosine hydroxylase. So as we turn our tyrosine into our noradrenaline and our levels of noradrenaline increase, this increased concentration of noradrenaline is going to be slowing down the production of noradrenaline. So it's going to be a negative feedback loop in order to produce the correct amount of noradrenaline. What did the chat say, Dave?
I'll answer the chat.
Okay. I can't see the chat.
So it's so Abhinav just asked, why is the parasympathetic long and the sympathetic short? And I wasn't quite sure what he meant. So he clarified by saying that the presynaptic part of the parasympathetic is long and the parasympathetic is short.
Yeah, so it's because
stuff, right? Yeah.
Because there's actually, like you learned this in Sem 2. Yeah. So it's actually like a sympathetic trunk, which is beside your spinal cord. And for sympathetic nerves, they actually they synapse at the sympathetic trunk. So that's why it's short. And that's why it's really long from the junction from the sympathetic trunk all the way to your organ. But for the parasympathetic, the preganglionic synapse is really close to the organ instead of at the synaptic trunk. Yeah, that's why it's the opposite.
Yeah. So if you can, there's no exact reasoning why that occurs. It kind of just is. But if you see my annotation, like really ugly annotation in the top right corner. So this vertical line here that I'm going to highlight in pink, you can imagine that as your spinal cord, okay? Like a really dumbed down version of that. And if we look at these first nerves coming from the spinal cord, what is highlighted in yellow is what we call the presynaptic neuron, yeah? Because it comes before this junction here, which is what we call a synapse or synapse. So this top image here is going to be your sympathetic nerves. So your sympathetic presynaptic neuron, or what is highlighted in yellow at the top, is going to be really short, whereas your parasympathetic presynaptic nerve is going to be really, really long. And then you can imagine like your organ here at the end, yeah, whatever organ that is. So it's simply a structural difference that you have to know between your presynaptic neurons, a structural difference for the presynaptic neuron between your sympathetic and your parasympathetic nerves. No real reason why, it just is. Sometimes it just be like that. Yeah. Did that make a bit more sense? Okay. Sweet, cool. Yeah. Okay. So, so we talked about adrenergic nerves, and we said that these are sympathetic. So they're going to be your fight or flight responses. So this is going to be the response you have, for example, when all of you were taking your interviews, your heart was probably racing, your palms were sweaty, knees weak, your pupils are dilated, your heart's beating through the roof, things like that, yeah? And so everything's kind of ramped up. And we can consider this in terms of their response. So that's called a sympathetic response. And to initiate these sympathetic responses, we're going to need two receptors, or two different types of receptors, depending where we are in the body. So we have our alpha and our beta receptors. We have multiple subtypes of these alpha receptors and multiple subtypes of your beta receptors. I'm so glad you got that reference. And these ones we'll talk about a bit more later down the track when you do a bit more of these adrenergic pharmacology things. But generally, beta is pretty easy to remember. We have two types of beta receptors that we know about, beta 1 and beta 2. And if you think about how many hearts you only have one heart. So you have beta 1 receptors on your heart. And how many lungs you have? We have 2 lungs, right? So we find our beta 2 receptors on our lungs. But don't worry too much about that at this stage. That's kind of just a look forward into the future. But essentially, if we activate these alpha or beta receptors, we're going to get a sympathetic response. So in the case for our gut, we have both alpha and beta receptors. And since it's a sympathetic response, we're going to be trying to decrease the amount of digestion we have, because from our body's perspective, that's not very important. So we're going to try to inhibit our gastrointestinal tract. If we activate our heart from our sympathetic nerves, we're going to have the increase in rate and the force of contraction. So you can feel your heart beating super, super quickly, and your heart will be squeezing a lot harder. So that'll help blood flow around your body so it can oxygenate your muscles and your organs better. Lungs, since you want to take in more oxygen, it'll dilate your bronchioles or dilate the path that your air takes so that you can get more air into your lungs. And then for your blood vessels, it'll be constricting your blood vessels. It'll be constricting your blood vessels because it doesn't want blood flow to unnecessary parts of your body, essentially. It's going to be trying to conserve the blood flow to your heart and your brain, and like the other associated important organs. So all of these will act towards improving the blood flow and the oxygenation of your brain and your heart. Okay. These are some probably a bit less important information, but noradrenaline can be released, the release of noradrenaline, sorry, can be triggered by amphetamines. So like your methamphetamines, things like that. So therefore, we consider our amphetamines an indirectly acting sympathomimetic. So we'll break down this term a bit more. So indirectly acting means that it's not the amphetamine that's actually acting at the receptor. And then sympathomimetic, you can break it down into like sympath. So that'll be talking about your sympathetic nervous system, and mimetic is to like mimic. So it'll be kind of replicating the effects of the sympathetic nervous system. And this occurs because your amphetamine triggers the release of noradrenaline, and your noradrenaline will cause activation of your beta and your alpha receptors, and therefore increases your sympathetic nervous system. So once this noradrenaline has been released, it has to get removed, right? Otherwise your heart will be beating super hard and super fast for, I don't know, to the rest of your life, right? So it's got to be removed. And removal generally occurs through reuptake. So it's kind of like a vacuum cleaner on the presynaptic nerve, and it will suck up all the released noradrenaline. And this occurs by uptake 1 terminal. That's just a name to know. And once it enters the presynaptic nerve, it has to be broken down by enzymes and then reused. So it's broken down by monoamine oxidase and COMT, which I'm not going to try to say. Monoamine oxidase, I think, is a bit more important when you consider some contraindications for some medications. So this whole process of reuptake can actually be blocked by cocaine. So if we block this process of reuptake, that means that our noradrenaline will be staying. Our noradrenaline will be staying inside the synaptic gap. And if it's staying there, it can repeatedly activate our alpha and our beta receptors to trigger the sympathetic nervous system. All right, so the question in the chat was, so is noradrenaline an indirectly acting sympathomimetic? So the drug, the amphetamine, like your methamphetamine, for example, from Breaking Bad, is going to be your indirectly acting sympathomimetic. Because if you think about your receptor here, noradrenaline is going to be directly acting on that receptor. So our noradrenaline is directly acting. But if our amphetamines increase the release of this noradrenaline, and that noradrenaline activates the tissue, whatever, we consider that methamphetamine or that amphetamine to be indirectly acting because it increases the release of noradrenaline. You increase the noradrenaline levels, and therefore your sympathetic nervous system is more strongly activated, if that makes sense. So your amphetamine is the indirectly acting sympathomimetic. Does that make sense? Yeah, exactly. So your amphetamine is the indirect sympathomimetic. Okay, so we've just covered our adrenergic nerves, and now we'll consider the other side of the seesaw, which is your cholinergic nerve. So at your cholinergic nerves, once again, at the presynaptic neuron up here, it's still going to be releasing acetylcholine. So the common theme for our adrenergic and our cholinergic nerves is that the presynaptic neuron will always release acetylcholine. You can see that in this case here as well. So our presynaptic nerve releases acetylcholine. So that'll be the same for adrenergic and cholinergic nerves. The only difference is that our postsynaptic nerve will actually release acetylcholine again. And this acetylcholine will act on what we call a muscarinic receptor or a nicotinic receptor. The way I like to group up these muscarinic and nicotinic receptors is that I think of nicotinic just being as responsible for your all your muscles, essentially. So when you're trying to go for a run, if you guys like running, acetylcholine will be released, at the site of your muscle, and it'll activate nicotinic receptors to cause contraction of your muscle. However, if acetylcholine acts on muscarinic receptors, that's going to be increasing your parasympathetic drive. So that's going to be increasing your rest and digest. So for example, after you've eaten, acetylcholine is going to be released throughout your gut or throughout your stomach, your intestines, things like that. And it's going to be causing it to digest the food that you just ate. So cholinergic nerves can either be to do with the autonomic nervous system, which is what your sympathetic and your parasympathetic nervous system falls under, or it can be involved with your somatic nervous system, which is what your motor, your voluntary motor control is to do with. Okay. So if we talk about acetylcholine, acetylcholine is synthesized from choline, and the enzyme responsible for that is choline acetyltransferase. Yeah, remember that. And then if we think about different innervations of your organs, if we think about the gut, yeah, so we want our gut to be active when we're trying to rest and digest, yeah? So we have to activate our muscarinic receptors, and that's going to cause an increase in contraction so that we can like squish up all the food and digest it, right? But if we're trying to rest and digest, we want to slow down our heart and we want to reduce the force of contraction because we don't need to pump around as much blood. So therefore, when we activate these muscarinic receptors, our heart is going to slow down. Similarly, for our blood vessels, since we can allow for blood to flow throughout our whole body, once we activate these muscarinic receptors, that's going to cause vasodilation. So your body is no longer trying to conserve blood to your heart and your brain, but instead it can spread out all your blood like to your hands, to your arms, to your legs, things like that. And that's all going to occur through vasodilation. There is a small exception though, because your muscarinic receptors won't directly affect your blood vessels. There's kind of like a middleman, and that occurs through nitrous oxide. But you guys will consider nitrous oxide a bit more at the very end of the year, I think, when you go through like cardio. Yeah, I have no clue what David just said, but yeah, through like cardio stuff. But yeah, okay. And then I talked about this a bit before, but skeletal muscle, contraction of skeletal muscle, so contraction of your biceps, your quadriceps, things like that, is through activation of your nicotinic receptors. Yeah, cool. So we'll kind of consider the response that comes from activation of these receptors. So we'll kind of go through the process of activating these nerves. So we have our nerve, yeah, we have our postsynaptic nerve. Yeah, we have our postsynaptic nerve, and this postsynaptic nerve has an action potential traveling down it. And once it reaches our nerve terminal or our axon terminal, there's going to be an inflow of calcium ions. And because there's an increased concentration of calcium ions in this axon terminal now, this is going to cause our vesicles here, which contain acetylcholine. These are going to exocytose. So they're going to fuse with the plasma membrane, and they're going to like vomit out all this acetylcholine. And this acetylcholine is going to diffuse across the synaptic gap, and it's going to attach to these receptors located at something we call the motor end plate. The motor end plate is kind of the name for the region where you have a ton of these receptors, a ton of channels, things like that. So the bit like right below the nerve terminal is what we call the motor end plate. And once your acetylcholine has activated your receptors here, so in this case for skeletal muscle, it'll be nicotinic. This acetylcholine will be broken down by an enzyme called acetylcholine esterase. So acetylcholine and it's an enzyme, so it'll break it down. And the reason we need to break it down is to prevent continual activation. Otherwise, what will happen is that I'll try to bend my arm and then I won't be able to relax. So it'll cause paralysis, and that'll be relevant a bit later. So once our acetylcholine binds to our alpha receptors and the two subunits of the alpha receptors, that'll cause ion channels, your sodium ion channels to open, and this will cause depolarization throughout your muscle, and this will cause contraction. So yeah, as I said, we have to remove our acetylcholine to allow for reactivation later on and to prevent us from being paralyzed. So it occurs really, really quickly. Okay, so knowing that our acetylcholine has to bind to these receptors in order to cause contraction, and it has to be removed in order to stop that contraction, we can consider two medications that we can give that will have relevance with this, with these nerve systems. So these are neuromuscular blocking drugs. So they'll block the connection, or they'll kind of interfere with the connection with our muscle. So we can group them up into non-depolarizing blockers and depolarizing blockers. And the difference between these two is that our non-depolarizing will be an antagonist. So they'll have, like they won't cause a change, essentially. They'll just block it. Whereas our depolarizing blockers will bind to it and it will cause activation. So if you first...
Sorry, just adding on to all of this, like it seemed like a lot, right? Like what non-depolarizing, depolarizing, it's like hard to remember like which one's which. But later on, you'll just realize that all of this, once you've seen it clinically, it's like pretty self-explanatory, because depolarizing just means like the patient has a full depolarizing movement. So all the muscles suddenly contract and they have like almost like a spasm movement, and then like suddenly they're paralyzed. And then whereas non-depolarizing, like nothing happens and then they're depolarized. Yeah.
Yeah, so it'll kind of be like a different appearance once you give these medications. So our non-depolarizing blockers will bind on. Oh, Jiting is here. Oh, hi, Jiting. Our non-depolarizing blockers will bind on and nothing will happen. So if nothing happens, what we can do to overcome this is increase the concentration of acetylcholine. And this will help because it's a competitive antagonist. So these acetylcholine molecules and our non-depolarizing blockers are kind of fighting for space on the receptors. And you win by numbers, yeah? If we increase our acetylcholine concentration, we're going to be able to kind of overpower our non-depolarizing blockers. Just some small points. It's not absorbed by the mouth. So I think you have to give it intravenously, I believe, and it doesn't cross a blood-brain barrier, which would probably be quite bad. So the drug, that you guys will need to know is something we call rocuronium. Yeah, and we'll talk about where you can find all these medications later on, if you haven't talked about that yet. And then if we compare our non-depolarizing blockers to our depolarizing blockers, it'll kind of be doing the opposite. So once it binds on, it'll activate our nicotinic receptor. And as a result from that, it overstimulates it. So because it's bound on and it can't be broken down, it's going to keep on opening the channels. And therefore it overstimulates it and it inactivates our sodium channels because they're not given time to recover back. The drug you need to know for the depolarizing blocker is succinylcholine. So rocuronium and succinylcholine are the main two NMJ drugs that you'll need to know. There are also a whole other, there's like a bunch of drugs you'll need to know. So namely pyridostigmine. So this is a reversible anticholinesterase. So an anticholinesterase will prevent the breakdown of acetylcholine. So therefore it'll increase our acetylcholine levels. And if it increases our acetylcholine levels, that is going to cause a decrease in our sympathetic and an increase in parasympathetic, because our acetylcholine is to do with our parasympathetic nerves. However, we mainly use pyridostigmine to overcome myasthenia gravis, which is like This is like a condition where you're just, what was myasthenia gravis? It's a condition where you can't move, I think. Oh yeah, it's a condition where you can't move. So it'll attempt to increase the amounts of acetylcholine to try get some skeletal muscle activation.
This is like Michelle Leach's like favorite part, because this is like rheuma, and she's pro at rheuma. She's like a rheumatologist.
Yeah, but this is not her favorite drug. We haven't got to her favorite drug yet.
Maybe true.
Yeah. And then, yeah, so atropine is anticholinergic, so it'll block our cholinergic things. So if it's blocking our cholinergic nerves, that's going to increase our sympathetic, and therefore we'll have some adverse effects of our sympathetic nervous system being activated. But once again, this is going to be indicated for our myasthenia gravis. Yeah, rocuronium is used as a relaxant, and so is succinylcholine, also used as a relaxant. If you think about them being a muscle relaxant, you'd know that there will definitely be a nicotinic receptor, because your muscles have nicotinic receptors on them. It wouldn't make sense for these to be muscarinic, because muscarinic receptors aren't found on skeletal muscle. Yeah, so with all these medications, you can find the core drugs on a website they call ePharmacology. So this is a website set up by faculty, and it will essentially list off all of the medication and all of the drugs that you'll need to know by the end of your 5 years here. So it's like there's, I don't know how many drugs, there are a ton of them, but kind of slowly go through the process. Yeah, so Jiting has just sent a link there. You log in with your normal Monash account. Another useful research is the Australian Medicine's Handbook, which is a very in-depth kind of view on different medications and like the adverse effects, the indications, the contraindications, the mode of action, things like that. That is very intense. But yeah, ePharmacology will give you a list of drugs that you need to know and the stuff, and kind of the relevant stuff there. And then quickly on envenoming, you guys had like a pre-recorded thing. So one point to take from here is venomous versus poisonous. So poisonous things are things like your pufferfish. So if you eat the pufferfish, you like freeze up and then you die. Yeah. So poisonous things, if you eat it, you will die. Whereas venomous things, if it eats you, you will die, because it kind of gives you a toxin or a venom that will break you. So poisonous things, don't eat poisonous things, and don't let venomous things bite you, because that's bad. And both of these, poisonous and venomous, will interfere with your neuromuscular junction. Yeah. So we can group these into three things: your presynaptic neurotoxins and your postsynaptic neurotoxins, as well as your myotoxins. Your myotoxins essentially break down your muscle, so you literally waste away. With the Australian Medicine's Handbook, there should be a link on the ePharmacology website where you can click through to the AMH, and by having a Monash account, you have free access to the AMH. Otherwise, it's like 150 bucks. Says we can't log into ePharmacology. Yeah, so that will just be like your student code. So for example, my email is pgo0003@student.monash.edu. Just scrap the @student.monash.edu, and it should work. Yeah, okay. So myotoxins will break down your skeletal muscle, so there's nothing to activate. Whereas your presynaptic neurotoxins will stop the release of neurotransmitter. And if it stops the release of neurotransmitter, that means you can't activate your skeletal muscle at all. Whereas your postsynaptic neurotoxins, it'll allow the release of your neurotransmitters, but those neurotransmitters won't be able to work on the receptors because they're blocked or they're broken. So presynaptic ones are slower, postsynaptic ones are faster. Not too sure why. But yeah, remember those 3 classes. So here's kind of, I think this is Jating's annotation of the diagram. So we have presynaptic neurotoxins, which are slower, and these vesicles here can't be released. Whereas our postsynaptic neurotoxins, they kind of block our receptors, kind of like an antagonist, and they prevent our neurotransmitters from activating the receptors. And then our myotoxins will just break the muscle down. So there's nothing to activate. And that is the end of...
That was taken directly from like active learning from last year. It was just like part of like, I guess, my notes, and all credits go to one Ashuni, yeah, for this diagram and everything. And I'm sorry for my terrible handwriting. Yep.
Yep.
Maybe you guys will do it too.
Oh, Zoe's here. Okay, cool.
Ah, Zoe got back from her run.
Yes. Hello. Sorry.
Wait, so okay, I don't need to do anti-cancer then, right? Like,
Yeah.
you're good?
All good.
All right.
Yeah. Wait. So did we only get a few anti-cancer drugs?
You're right on time.
Wait, didn't we start at 7:30?
Yeah, we did Kahoot, bro.
All right. All good.
Yeah, and Adrenergic and Cholinergic took like 10 years.
Oh, okay. Cool.
Yeah.
Thanks, Peter.
Oh, good.
Yes. Sorry, I am late.
Oh, good. Zoe went on a run
really
and ended up 9 Ks away from home. Ended up 9 Ks away from home.
By accident.
By accident.
Anyway, completely unrelated. Just going back to the whole ePharmacology AMH and useful resources for pharmacology. ePharmacology is really, really handy. There are heaps of really nice some like drug summaries on the like Google Drive, and I actually have a small summary of drugs here as well. But I actually do recommend that you go through each drug on ePharmacology individually. I think some people might disagree with me, but I personally found that actually making the table myself was a lot more helpful than just passively reading other people's notes. So that's that. And for people who may be interested, as Jiting mentioned, there's also there's the AMH on the right-hand side here. Another useful resource is the therapeutic guidelines. So if you actually, for some reason, want to check out the different dosages and actual drugs that are used for different conditions, you can search up, hypertension into ETG and stuff like that. Anyway, actually getting started. So I'm presenting on anti-cancer drugs today. In first year, it's basically just a lot of memorization. And there's really not too much to this other than the fact that you need to remember that cancer is an abnormal, and this is from Peter's slides, by the way, is an abnormal and uncontrolled division of cells. So basically you have a bunch of cells which are just growing, dividing really, really quickly and really, really out of control. So they're dividing more quickly than normal cells in the rest of the body. And it's that we use that, rapid division that we use to, target cancer cells. Selective toxicity is very important. So you want to have drugs that only target and only kill cancer cells and don't, kill other normal cells around them. This obviously doesn't work too much because chemotherapy has massive, massive side effects. And yeah. Treatment complications. So common adverse effects with drugs are mostly associated with rapidly dividing normal cell populations. So with skin, you have, your epithelium constantly sheds and regenerates itself. So, and that's the same thing with the GIT, hair constantly regenerating, and same with the sex cells. So those ones are the ones that can be targeted using the cancer drugs. Cancer cells can also be toxic to the organs, so bad for the heart, nervous system, kidneys, urinary bladder. That's not really that important. Okay, classic cytotoxic agents. So basically, all the ones on this side, so the alkylating agents, cytotoxic antibiotics, antimetabolites, and this histone deacetylase are things that interfere with like DNA synthesis, or they interfere with transcription translation. You don't really need to know the details about these processes, just kind of know that they exist, and like maybe like these 2 dot points for each. Plant alkaloids, I don't think you really need to know. I don't think there are any drugs on the core drugs list, so just kind of forget about that one. Okay, novel anti-cancer agents are like mostly used for breast cancer. So these ones include your hormonal antagonists. So in breast cancer, you have certain types of breast cancer that like kind of use estrogen as fuel, or that's a like ridiculous oversimplification, but you can think of it as fuel. So these selective estrogen receptor modulators kind of block those receptors and stop the cancers from growing. And that's kind of similar to the aromatase inhibitors, which inhibit aromatase, which produce estrogen, and that kind of reduces the estrogen as well. Glucocorticoids aren't really that relevant in this case. Okay. Other supportive therapy, you don't need to know this in first year, but because it's interesting, we all know that chemotherapy makes you very nauseous, makes you vomit a lot. So you can take antiemetic drugs, which means drugs that stop you from vomiting, and those include these drugs, and you actually don't need to know them all. And you don't need to do these ones, but just for interest. And these are the different drugs you need to know for first year cancer drugs. So you've got cyclophosphamide, doxorubicin. I'm not actually going to go through these because I think that, you know, drugs are something you kind of need to make flashcards on and just memorize. But this is just a resource you can have a look at. And same thing for this. And yeah, that's basically it. Yeah. Any other comments from anyone? Wonderful. But yeah, just make flashcards and constantly revise them throughout the year. Yeah.
Yeah, so like how I do my farm is like I'll make my table and I'll essentially use like image occlusion to block out like your mode of action, block out your adverse effects, block out your indications, and like I'll go through that. So that's like one way you could do it. Other people, they make stories out of each drug, so it makes memorizing each drug a bit easier. But yeah, it's a bit of a mix depending on.
An example.
Yeah.
Wait, sorry. I just want to show a quick example of how you could set it up in Anki. So I use Anki quite a lot. So let's just use close deletion in this case. You could have, this is really good. So I would have the drug name at the top, and then that could be like drug class, and mechanism of action. And then not all of this will be bolded. And then I would have like adverse effects. And I might have like indication at the bottom. So what is it used for? And then that'd be like for cancer. And then what I'll do is I would actually lock all of these out. So if I wanted to actually review this flashcard, like each time, the one of them will show up as, you know, blocked out, or it won't, like it'll be like blue, and you won't actually be able to see what it says, but then you'll be able to see the rest. And then you just like, you know, try to guess what, or you just actively recall what the drug class was, and then you'll be able to see if you're correct or not. And yeah, but Peter has a different method, which is very effective as well.
Wait, what software is that?
This is Anki, so it's like not online, but it's a flashcard app. Very, very helpful. Highly recommend. I use basically everything.
Yeah, Anki is like, it's a flashcard application. You can get it on your phone or your laptop. It costs money for iOS as an app, but you can still use the web version. And it's essentially like flashcards, and then you rate your confidence in knowing the answer from like bad, good, I don't know, like there are 4 options on multiple times, like when you do it later down the track, and it'll show that same flashcard at a predetermined interval in order to like counter your forgetting curve.
Just watch Ali Abdal's video, like.
Yeah.
Yeah, so these were like my first year like physiology ones. So what is neuromuscular junction? Obviously, I haven't gone through this in a very long time, but like
So
you can see
like,
that it has different periods. So that kind of reflects, you know, how long it's been since I last.
Also, some people don't want to buy the iOS app because it's like $32, but like med students buy so many textbooks that are useless. And if anything, the app is so good. Like by getting the app, you can just do it on the public transport if you're busing later on and stuff like that. Like it's actually a worthwhile investment. Like $32, you know, support the developers. We're ethical individuals here.
Or you can just open your laptop on the bus. Same thing.
She's right.
Yeah, that's true. Spend your money however you want to spend your money. But for lots of us, like we find it's useful enough to what's the word? To like
justify the purchase.
Yeah, that's exactly what I was going for. Okay. Yeah, maybe we'll like, I don't know, make a post about Anki sometime. Who knows? But yeah, so we'll be going through HKS next. So this would be like a fairly important topic, I would say, access to healthcare. And it's going to be mainly focused around a specific model called Tanehashi's model of some sort. Before we get into that though, we'll be thinking about health equity. So if you think about your hospital, if you've ever been to the ED, you'll know that once you show up to the ED, you're going to like go up to the nurse or like the triage nurse, and they're going to essentially rank your importance of how urgent your care is. So let's say if you have a splinter that hurts like a tiny bit, but it's not that urgent, you're probably going to be way down the bottom of the list. But if you compare that to if you're having like chest pain, you're going to be like sent right through to the doctor's office. So the health system is based off equity and not equality. And that allows for the care and the provision of care to those who need the care most, and kind of achieving an equal level by giving a different level of care to a different person. So although that can cause some people to lose out on some healthcare, there are additional barriers that make even accessing the healthcare really, really difficult. And we'll be talking about the Tanehashi framework. So here, this is like a model that goes down by population sizes, and it talks about how the covered population or the population that is able to access the healthcare decreases as we introduce these various barriers. So target population is, for example, the whole of Melbourne, yeah? We want to cover the whole of Melbourne so that everyone gets healthcare, yeah? However, for some people, this healthcare isn't available because of various factors which we'll go through. So therefore, only some people can access it. And then some people, they can't get to the hospital. So even smaller subset of those people can access the healthcare. And then to some people, this hospital is a touch racist. So some people don't want to go there. So therefore, the population that is able to access it is even smaller. And then we consider those who actually use it. So those who actually go, and then it's even smaller. So out of our whole target population, we're going to have a really limited population that's going to be able to go to these services. So we'll be going through like these different stages or these different levels in this Tanehashi framework. So if we define each of these different stages, we have availability as kind of like the first limiting stage. And this is who the service is available to. So can I actually get there? Does it exist there? If I'm living 500 kilometers away from Melbourne, is there a hospital near me? And then we think about accessibility. So although I have a GP office down the road, does it cost $500 per visit? Maybe. So therefore, it may not be accessible. And then acceptability is to do with culture. So are the staff sensitive there? Are they culturally appropriate? Things like that. And then contact is the group of people who actually access the services. And then effective isn't really to do with healthcare access, but it's to do with the actual treatment quality. So is it evidence-based? Is it good quality? How do doctors practice? And how does that practice affect the efficacy of their practice in improving the person's condition? But it's not all on the doctor's side. Sometimes this can also be affected by the adherence to treatment. So although the doctor might give some medication to the patient, if the patient doesn't take the medication, then the treatment's not going to be effective because they're not taking the treatment. So we'll kind of be looking at a few of these factors in terms of some Australian health issues. So availability. The main one to talk about here is urban and rural areas. And I'm sure a lot of you know the disparity between here. And there's kind of a paradox because there's because there is more disease in a rural area. However, there are fewer doctors, whereas in an urban area, there's less disease, but there are more doctors. So you have this paradoxical combination between disease and doctor. So therefore, as a result, you get poorer healthcare and therefore poorer health status. And this still stays here despite some policy changes. For example, the bonded medical placement scheme, which is meant to increase rural doctors, but that's not quite enough. So therefore, the Australian Medical Association recommends a few things. So they're recommending like community residency programs. So doing your residency or your specialist training in a rural area, increasing the rural intake, and increasing the role of certain other allied health professionals. So pharmacists can do more. We have physician assistants perhaps coming in and nurse practitioners. So these are still allied health, but they're able to do more and therefore fulfill some of the lacking healthcare. So this is aiming to increase the availability. Then we consider accessibility. This is to do with financial difficulties and physical disabilities. So although there may be a GP clinic, does it have a wheelchair ramp? Can someone who is in a wheelchair access the healthcare there? So this is mainly to do with like disabilities and things like that. And by having a disability, sometimes it's also going to affect your socioeconomic status. So it can be like a double whammy in your ability to find healthcare. Yeah, so accessibility is whether or not you're able to like pay for it, whether or not you can actually go there. Acceptability is to do with culture. So if the patient considers a doctor's practice to be culturally appropriate and culturally safe, they're actually more likely to go there and they're more likely to get help and stick to that treatment. And therefore, this is going to improve the effectiveness and improve your health outcomes. And then the opposite if it's not culturally safe. And yeah, unfortunately, there are policies that do discriminate against certain groups. So that can prevent our healthcare from reaching everyone it really should. And then we have nutrition, which is HEP. Everyone loves that. Where did RJ go? Did you say anything?
I have no idea.
9:15. Oh, well, I'll probably cover it because he said he'll be back at 9:15. Yeah. Don't we just cover it?
Yeah, if you want to. I mean, what
or
is
do you
it?
want to cover it? It's nutrition from HEP.
Okay, I don't mind doing it.
Okay, sure. Do you think we'll take it?
Well, I haven't looked through this in a while, but let's do it.
Yeah, it's fairly short. Just a lot of stats as usual.
Yeah. So welcome to the nutrition part of HEP. And these slides were prepared by Heini, but unfortunately she can't be with us tonight. Okay, so these are just some key stats. So the main key stat reflects that only 19% of medical students, when surveyed, actually believed that they have been extensively trained in nutrition counselling, and out of those 19%, only 17% of these students would actually counsel their patients regarding nutrition. So like the take-home message here is that, one, most medical students believe that they literally don't get taught about nutrition. And a lot of the times as medical students, we think if we don't get taught something, then it might not be important. And so therefore we realize that a lot of medical students in the future, when they do counsel patients, don't actually bring in nutrition as a major lifestyle factor that their patients should change if their diet is bad. And so these are a few dietary guidelines. So eat whole fresh food, make sure it's varied and well prepared. Try not to eat too many empty calories, so things like candy. Try keep it mostly plant-based, and don't forget to drink water. So pretty self-explanatory. So as for nutrition, food plays an important role in the prevention as well as the management in a lot of chronic illnesses. And so that's why in your history taking, in your social history, you do often ask the patient how their diet is, because an unhealthy diet, such as a diet that is high in fat and meat with little vegetables, for example, can put a lot of people at risk for certain cancers and cardiovascular diseases, etc. And also people with these chronic illnesses, maintaining a good nutrition will essentially improve their future outcome. And so we do have to realize that globally, on average, there's essentially an increase in weight. So people's average weight is increasing. And Heine's has said in the top corner there, so don't have to remember all these stats. You just have to know that in general, Australia is doing pretty shit in terms of gain weight. So some of the stats to reflect these include 2.3% of the world's men and 5% of women were severely obese. This is when their BMI was above 35. And the prevalence of morbid obesity was 0.64% in men and 1.6% in women. And this was back in 2014. And given the trend that we see, it would be higher by now, so 2020. And this here, the CSIRO Healthy Diet Score, this is actually, I'm pretty sure it's a test, an online test that you guys can actually do yourself. It takes a while, but if you want to do some active procrastination, you can go ahead and see how healthy your own diet is. And essentially only 80% of the participants received a score of around 70, which is essentially benchmark. The average score was 59 out of 100. And typically you see women have better nutritional scores than men, but not by much. So only 60 versus 56. And quite a few adults aren't eating the recommended intake of fruit, and 66% of people aren't getting enough vegetables in their diet. And so you will learn a few certain diets as well as nutritional substances and how they can impact our health. So the first one is omega-3 fatty acids. So this is often found in your fish. And this is the most effective therapy for reducing all-cause and cardiac mortality. You also have a diet called the Mediterranean diet, and it essentially showed a 72% reduction in cardiovascular events attributed to this diet. And it's also protective against diseases associated with chronic low-grade inflammation. So these include things like cancer, diabetes, etc. And it's also associated with longer telomeres, which Craig Hassard loves to talk about. So in general, just know that the Mediterranean diet is a pretty good diet to be on. Another one is the Ornish diet, and this has shown to downregulate prostate cancer gene expression. The quality of life dips initially when you first go on the diet, but it improves over time as the benefits kick in. I think pretty sure Craig Hassard will also go through a few more other diets, but Heine's just included a few of the main ones, especially the Mediterranean diet. And as for nutrition and its effects on cancer, here are a few things you should kind of remember. So the first one is processed meat, and it's recently been classified as a group 1 carcinogen. So it's up there with things like tobacco. Obviously, within your group 1 carcinogens, you have worse ones and better ones. So processed meat arguably is probably not as bad as smoking, but it's still in group 1, which means it's really bad. So red meat is also likely to be carcinogenic, but especially if it's processed. And as for breast cancer, Heini said, don't really need to know the stats, just know what diet that helps. So with breast cancer, a low-fat diet is seen to help, and it's associated with essentially a 24% reduction in recurrence, and also has a 19% improvement in survival after 5 years. And also seen patients with the highest intake of soy protein also had a lower risk of death and also a lower risk of breast cancer recurrence. And vitamin D has also shown to help reduce mortality. Yes, and also cruciferous vegetables. So these guys are pretty important. So these guys are like your broccoli, your cabbage, your Brussels sprouts, and your cauliflower. And these have been shown to be most protective against cancer. So do remember to eat your cruciferous vegetables. And also, quick note at the bottom, try to avoid the use of supplements. It's best just to obtain most of your antioxidants and nutrition from your diet. So don't eat a bad diet and then take supplements to get your vitamins and antioxidants. The best way is to get it directly from your diet. And a quick summary about telomeres. Again, because Craig Hassard loves them. So here's a list of substances that either lengthen or shorten your telomeres. I would recommend memorizing a few, but once again, most of this is common sense. So substances that lengthen your telomeres include your vitamin D, C, E, folate, and your omega-3 fatty acids. And substances that shorten your telomeres are also pretty self-explanatory. So smoking and processed meat, which are very bad carcinogens, having a high BMI, high homocysteine, when you eat a lot of red meat in the absence of starch, and also if you drink sugar sweetened drinks like your Coke, for example. And since it's HEP, of course, we have to bring in mindfulness. So there's something called mindful eating. And so this is essentially slowing down, chewing more, tasting your food, and really being in the moment when you eat your food. So don't think about other things when you're eating lunch, for example. And this has essentially shown to reduce unnecessary food intake. It's shown to increase enjoyment and satisfaction of your food, so you actually enjoy eating. It helps to aid in digestion. Often people will improve their food choices when they undertake mindful eating. And it also puts us back in touch with essentially what our body requires. And this can be useful in the management of some binge eating disorders. And I think that's the end of nutrition. Yeah.
Yeah, cool. I think that's the end of everything for the slides.
Yeah.
So yeah, I think we'll be making a post probably, I don't know, in the next couple of days, just looking at just like fixing the mistake on the Kahoot, and then fixing the mistake on Kahoot, maybe a bit about Anki, and probably just like going over the ePharmacology website, and maybe some pharmacology drugs. Sorry, not pharmacology drugs. Some of the tables that we use for Anki, if that's something you guys would find useful. Yeah, anything to add?
Not really. Just like a quick warning though, like if you do choose to make your own Anki cards, they can take a bit of time to actually make them, but once you get over making them, and if you actually decide to use them, they can be pretty helpful. Don't be the person like me who makes them, uses them maybe like 2 days, and then kind of forgets about them for a long time, because then you kind of wasted your time making the Anki cards. You might as well have just stopped at taking notes.
Yeah.
And if you want to suss around on the internet, there are like pre-made Anki cards made by other med students who have shared them online. The only downside to using pre-made ones is obviously not all the content on there is going to be relevant to you, especially in your first sem, which is all kind of more biochem related. Later, when you get into anatomy, pre-made Anki cards by other people can be a lot more helpful and less time wasting as well.
Yeah. Yeah, Anki's like like once you make the cards, you're going to have, I don't know, depends how many you make. Like you could have hundreds to do on the first day, honestly, or 50 new cards like every day for like a few days. So the start is going to be rough, like rough. Like you're not going to have a good time. But after like the first week or so, then it starts like the revision number or the number of flashcards you have to do every day reduces. So it makes life a bit better. But yeah. Sem 1 for pharmacology or for content? Because it changes a bit for different people, just in general. I used Anki for pharma. Well, Anki for pharma and like the gritty bits of biochem, that just weren't possible. Otherwise, I use something called, it's just active recall. Actually, fine, I'll show you guys. So for example, I'll share my screen, I guess. You guys can see my active recall, but it's essentially like you write your notes for your, thingy, for your content, and then you turn it into like a question. So for example, this is all content that is not relevant for you guys, by the way. Don't use this. So for example, like how many nephrons are formed after birth, which is in your kidney, and you think, let me think about that. None are formed after birth. And I take a look at the question, and I see the answer, and I'm like, okay, I knew that answer, so I put it as good. And like after going through a few rounds of that, you can kind of get info into your head. That system is kind of based off Ali Abdaal. But yeah, like it depends. Different people study in different ways. Some people find diagrams really useful. I don't. Yeah. Jishing, how did you study?
Sim 1 was just notes.
Yeah.
Yeah, and my whiteboard, and that was it. Like I didn't do anything special. Like you don't have to do anything special if it doesn't help, because there's always a learning curve for these things.
Zoe, any ideas on how to study?
Well, I mean, I kind of drop kicked someone, to be completely honest. Sem 2, I did a lot better in. And that's where I kind of brought in Anki, because the thing about Anki is that like it's a bit annoying sometimes, but it really forces you to study things. And yeah, we'll do an Anki session or like a brief overview on Anki maybe a bit later.
Yeah. Just questions in the chat. Anticholinesterases. So anticholinesterases are, it's an important concept to understand. So you have your presynaptic neuron.
They decrease the breakdown of acetylcholine. So they decrease the breakdown of acetylcholine, then you have more acetylcholine activating the cholinergic receptors for longer.
Yeah. And those cholinergic receptors can either be muscarinic or nicotinic. So anticholinesterases increase acetylcholine levels and therefore increase activation of those receptors.
Yeah, it's very important. No, drug names for anticholinesterases. What anticholinesterases do we even have? Just rocuronium.
There was one in the table.
Yeah, pyridostigmine.
No, that's not anticholin. No, yeah, it's pyridostigmine. Yeah.
Pyridose. Yeah.
You can see how well I know this.
Pyridostigmine is a reversible anticholinesterase. That one. I think that's the only one.
Pyridostigmine is. So basically, if you want to know the drug names you need to know, you just go to ePharmacology. If it's there, you learn it. If it's not, you don't need to know it. There are heaps and heaps of like drugs within the same drug class. So you've got like ramipril. I don't know, it's terrible. I don't know any other.
Ramipril, perindopril, like all of those like are the same ones. Those drugs you haven't learned yet. Just
yeah.
And
you only really need to know one out of like that drug class, or maybe like one or two, depending on what's in ePharmacology.
Yeah. So I'll show you guys ePharma. So when you log in, you can look at the side panel and you can see the MBBS, which is like the old name of our course, Bachelor of Medicine, Bachelor of Science, Surgery. So this list here is going to be very daunting because this is the list you need to know by the end of 5 years. Doesn't sound that fun, right? So don't use this here because that'll just overload you. But instead, come over to the side and look at the core drugs for each different system. So right now, or for the things that you'll cover in Sem 1, you'll be looking at musculoskeletal as well as infection. So in musculoskeletal, what? Wait, am I in the right place? DMARDs, gout, NSAIDs. That's not right.
Wait, what are they doing again?
They're doing NMJ.
NMJ is kind of tricky because it's scattered basically everywhere. There might be some in CNS. Oh, actually, no, I don't think there are.
Yeah. Yep, some in central nervous system for myasthenia gravis. Core drugs. Core drugs for myasthenia gravis is pyridostigmine. Yep. And it'll go through like a mechanism of action. So pyridostigmine is an anticholinesterase, first line for myasthenia gravis. It increases end plate depolarization and causes muscle contraction. Yeah, but like as you when you guys start infection, like your antibacterials, antifungals, antivirals, you'll have these kind of categories. So you can see that all the antibacterial core drugs are this fun list. Your amoxicillins, cephalexin, cipro, clarified, doxy. Yeah.
But yeah, like you can freak out about this, but the fact is, basically, if you do like 3 practice exams, you will have seen all the questions that will show up on your exam before. They reuse the questions like crazy, and all the year levels have already thought up all these like different mnemonics that can help you remember like the key, information that you actually need. So it's actually not too bad. Like pharmacology is actually quite easy because you're just remembering what the answer is.
Yeah, not something to stress about right now. Like right now, you're going to get like this huge list of drugs to know, right? And it's going to be so overwhelming. Yeah, because I remember like when we were doing these, I was like, what the heck's an adrenergic and cholinergic nerve? And like, what are all these drugs that sound all the same? But yeah, like eventually you'll see the common drugs they test. They don't even test these neuromuscular ones that often, I don't think. They just like testing your antibacterials, like your doxy. Yeah. So nothing to stress about right now, I think, especially given that you don't have exams. It's a formative quiz for you guys as well. Yeah, I'll just try to slowly figure out what your studying style is. But even if you don't figure it out, you have like 2 years to do it. So yeah. Yeah, we might do like a how to Anki kind of session maybe sometime in the future. Would that be useful for you guys? Or like a how we study kind of thing? Yes, yeah. Oh, okay.
Oh, seems like that's a popular idea.
Okay, yeah. Okay, we'll do that. Okay, thanks. Cool. Does anyone have any questions to finish off?
Ajay.
Hey.
Yeah, Ajay's back. Hello. Yeah, maybe coming into exams would be good. Okay, yeah. Even though they're formative, that's true.
Oh, are we done?
Yeah.
Yeah.
Like week 8's not that long.
Yeah.
Yeah.
Right.
What's week 9? What's week 9?
I don't know. But yeah. Thanks for coming, everyone. we'll let you know what's happening in the future on our group. All right. See you guys.
Yeah.